I am MuscleNerd. I'm from the iPhone dev team. There are actually a few other dev team members in the audience, but I won't point them out. We operate that blog there. We've had it for about since 2007, or a little bit less, 4 years. 133 million visits so far. I initially was actually on a different team called the iPhone Elite team. When I came to the iPhone dev team, I was more interested in baseband, although nowadays I do some jailbreak stuff too. I was fortunate to be tech editor for this iOS Hacker's Handbook, which came out a few weeks ago. Some of the authors of that book are also here this week. I'm going to dive right into it. I'm going to meander a little bit, but by the end of it, you'll see that there was a path that I took. Just some real basic stuff. The baseband is obviously it's the embedded CPU that's responsible for the cellular part of your phone. You talk to it, or you typically talk to it over the low-speed UART or high-speed USB, or of course the cellular network. It's kind of tough to. It's a lot tougher to work as far as exploits development goes because it's there in front of you, but you don't have the keys and you don't have the screen, and you know you're talking to it, but it can crash at any time, and then as soon as it crashes, you lose your USB. So it's very touchy-feely. So it's a little bit more difficult than the main CPU to work with crashes. But luckily, it does have this saving feature where when it does crash, even if you lose communication with it on its way down, it'll save the reason for the crash in the NVRAM, and you can pull that at the next reboot. The logs are not very detailed compared to the iOS side of things. You don't get symbols or anything like that. You just get a basic system stack dump in the registers. At least, well, this is the 3G crash log. They beefed it up a little with the iPhone 4. There's a lot more information on there, although ironically, a lot of this information doesn't relate to the crash. It relates to the crash handler. So it's redundant and not very useful. But there are some bits and pieces on there that you can use to help you figure out why things crashed. The baseband's kind of interesting because a large part of it actually executes in place from the flash memory space. So they don't need as much memory as they would otherwise, but I feel that there are some security reasons for keeping things running out of the flash space. Not everything runs out of the flash space, but the advantage when you run out of the flash space is you get this automatic protection. You know for sure that nobody's going to be patching your code if you're sitting in flash, because things will come crashing down. So there's no need for some of these features that are on the iOS side of things, such as ASLR and the write, execute, exclusive OR stuff. There are little bits and pieces of the flash that are writable, but that's typically for things related to tokens and small little bits of information. There is one part when the baseband first starts up, it does actually go off and pull big chunks of that code and puts them into fixed locations in RAM. And that's called scatter loading. It's a typical embedded thing to do. But you get to influence, or you, not me, but Apple, the compiler, gets to influence, gets relocated. Maybe I read too much into things, but again, I think there are some security reasons for keeping things in flash. I've actually seen, the parser, the big AT parser, which is a humongous routine, the largest routine you've ever seen, does sit in flash. I think that's more for space reasons. But I'm going to talk in a second about a case where I've actually seen from RAM back to flash. This is a funny, so when I was preparing this talk, I started to realize there's a lot of anecdotal stuff. There's a lot of interesting things that happened in the history of unlock development. And we've always been pretty paranoid about telling these stories because, in the sense, you don't want Apple to know that you found this stuff, and you always hope that it's going to come back in some sense. But here's something that was pretty interesting during the first iPhone 2G. We found for 12 or 13 of the baseband updates that actually they were embedding in the image of the baseband. They were embedding a pretty detailed change log of the reasons for the baseband update. And they were just human written comments, you and I would write. And they were accompanied, they were comments because they were next to lines in the code that were used to pull that compile together, but still, they should have filtered out the comments and just left the lines of the file names in there. So we were able to glean a lot of insight into the early baseband because of the comments that they left in there. And it's pretty interesting because those comments themselves in the zipped form were actually flashed into Flash along with the rest of the baseband. It just must be some weird artifact of this clear case compile stuff that they were using. Here's an example. This is just one I picked at random. A lot of them it turned out a lot of them are related to things like signal fidelity and things like that, but that second one's pretty interesting because it just goes off and points you to that EEP, part of the code to look for a way to crash the baseband because, they're looking at it themselves because it's posing a problem. So this slide is about, there's a lot of, I guess, for reasons to do with you want to test what you give to the end user. There's a lot of routines in the baseband that you and I don't ever use. They're all calibration related or diagnosis, and if you have a specially provisioned device, I presume that you can use software to go off and collect this information from this part of the baseband. But you and I never use it. In fact, for normal phones, all that stuff is disabled. And it's disabled through tickets or SIM cards or some mechanism. But in the end, it really just comes down to a flag whether or not you're allowed to use those commands yourself manually. And so if you can, it actually helps a lot if you can just get a very simple exploit in there to just flip that one bit. You don't have to do a whole lot because once you open up that whole interface, all of a sudden that interface is very rich in features and diagnosis and it lets you peek and poke into memory and all sorts of stuff. So it really helps. It's not very useful. It wasn't very useful for an actual unlock because we didn't want them to know that we were changing this bit. We didn't want that interface to go away. So we used it for development of the unlock just to make the process a lot smoother. But in the end, we ended up, for every unlock that we did, we would distill a final solution from it and just leave this interface be and not let them know that we were using it for this purpose. This is one of those things, bottom part of the slide. It actually was very nice because not only was that bit allowing you to use the commands, but the command tables themselves, as opposed to being in Flash, they were tables sitting in RAM. So you could use those vectors as ways to run your own code. So we created like 4 or 5 different core routines that we would then assign to these. We'd co-opt these command tables and use them for our own custom routines. Again, for unlock development, not for the final product. This is an example of the type of interface, and it's a very complex interface. I mean, it's really user-friendly. It's a lot more user-friendly, ironically, than the normal baseband that you'd interact with. And I guess that's because engineers or something were interacting with this interface in the field. So there was a very complex help system, and you could see all these funny little structures that you could declare, and it was almost like a very useful language in itself, although a little bit cumbersome. So here's an example of a thing where you're creating a sequence, and I guess the sequencer is just used because you want to sequence through a bunch of events to cause some network behavior. So here's an example of just creating our own arbitrary sequence and just doing silly things with it. And then at the end there, you do that final run. And even though our sequence was just a little for loop with some print statements, there was obviously a much more technical reason to use a sequencer. This bottom line right here is an example where I've created my own command, like I was referring to before. So that MW command is code. It points to code that I've used the fundamental exploit to inject into the baseband. And so then I've assigned that MW command to one of these tables for the cow routines. And now I can just write an arbitrary amount of words into memory. So there I'm writing 16 words into that address. Again, for speeding up things. Switching topics. AT commands, there are hundreds and hundreds of AT commands that are in the baseband. Many of them are actually still vulnerable. As you know, when you use these commands for unlocks, they get fixed. But there are at least 3 or 4 that I know of that are there. And it drives you crazy because they're there, but they're disabled with a simple bit mask. And what they're doing is they've taken an inventory of the commands that they're using, because I guess these are 2 different, you've got Apple and you've got the baseband vendor. They're all throwing stuff into it. And it looked like Apple's trying to not want to worry about stuff from the vendor. So they're turning off all these various commands because they don't want to have to worry about them anymore. So they started doing that. And I think, here's an example. It's something like 540 bits of a bit mask. And it's about equal. There's about 250 that are enabled and about 250. Actually, it totals up to 400, I think. So it's like 200 and 200. So you can see all these commands, all these ones are commands that are in the baseband taking up space, but they don't want to have to worry about them, so they disable them with this one bit mask. So they're there, but you can't use them. But ironically, I can go in to a vulnerable baseband with some other exploit and clear this mask completely to all zeros, and now all the commands are there. So I can actually test that the commands that are disabled would still be useful if only they were enabled again. So try to come up with a way to want them to be enabled. I'm going to skip through this stuff because it's been talked about before and another talk of mine, and we're running late. But this was basically just talking about the very first baseband was broken in many ways. The first baseband, there was a pretty good vulnerability found for it. And then we found an even better one, and then we found an even better one after that. So by the end of the day, it was just completely owned in every way you can imagine. There were 3 or 4 different ways to just completely take over the device. And it was all hardware determined, so there was no way to fix it. This boot neuter thing was a little app we wrote to just have fun with the baseband, basically. You could put arbitrary payloads in there. So I'm going to talk a little bit about the Ultra Snow real quick, just because it's interesting. This is a list of the tasks, the typical tasks that are running in the baseband at all times. It's listing the task names and their priorities. There's about 70 of them. They're all passing messages to each other. They're not like calling each other, they're not invoking each other, but they're sending messages, either short or long messages to each other, and just interacting that way. It's mind-boggling when you think about all the unpredictable ways that this stuff is interacting with each other. So what Ultra Snow Unlock does is it intercepts one of those messages, one of the critical messages. So what we did is we sat there, we figured out what tasks were involved with the unlock, and we just started watching what messages were going to and from that task by basically taking over the semaphore in control of those messages and just seeing who was calling it at what point. So in blue, you see the security task and the SIM task. SIM is just basically the hardware task interacting with the SIM reader, and SEC is obviously security. So what we observed is we could sit there and watch this message passing, and we see all these, very obvious messages being passed from the SIM to the security task. And the one that really matters here is this compare lock data, and that has that header of 13 or D hex. So what we did is basically whenever we saw that message go from the SIM to the security task, we knew that the unlock query was in progress. And so what we did is you can't probably see it, it's pretty tiny text. But we basically stole that message. We sat there, we sat at a higher priority than the security task, and we robbed that message because we were at the higher priority. And when we saw it was this 0xD message, we mutated it. And we tricked both ends into thinking that we short-circuited basically the decision. So we had to forge a lot of that code is just forging the results that would have happened if a normal unlock sequence had taken place. We were able to use the exact same sort of concept with the iPhone 4 in the very first baseband for that. But at that point, we started what was nice about the iPhone 4 is that all these nice little messages there on the right, they were clearly in the error messages of the new baseband. We had no idea up until that point really what the functions were. We were labeling them, A, B, C, D, E. But once in a while, they imbue a lot of information into the error strings of the baseband. So we saw that with the iPhone 4. But we also saw they were started to, at that point, they started to look for mutated messages, which of course would never happen in a real embedded system. You never have to worry about somebody coming in and mutating your message on the fly. But they went off and actually looked for it. You can see here, they're sending a message, they're waiting for the response, and then when the response comes back, they're checking that the original message is the one that they sent, which is a little bit overkill for a normal embedded system, but, and we were able to just bypass that anyway using some other tricks. So even though, and they spelled it wrong, they spelled it timbre instead of tamper. Many times, like 16 different times. New topic. SIM interposers are sort of big lately. They've gone through phases very early on. There were SIM interposers, and when I say interposer, I mean a little hardware carrier that you stick your SIM into, and then you stick that combination into the single SIM slot of your phone. And what they can do is they can sit there because they're in between physically in the electrical path between the SIM card and the baseband. They can play tricks with the messages that are being passed to there. So obviously the baseband wants to go off and query the flash on the SIM to get its keys and things like that, and various activities that happen when you do a normal connect to a carrier network. What they can do is they can play games there. And one of the very first financially successful interposers was the Turbo SIM. And it starts around the middle of that slide. They, at that time, and for a surprisingly few number of updates to the baseband, they did not actually fix this problem. But what would happen is when the SIM was first inserted, there'd be 3 different queries to the SIM card for its IMSI. The first 2 were completely related to determining whether or not to even talk to that SIM card in the first place, which is essentially what an unlock comes down to. And then only the 3rd one was actually used to negotiate with the tower to get onto the network. And so what the SIM interposer was able to do is fake it out. They knew what carrier that phone was meant to work with, and they just pretended to be that carrier for 2 of the 3 messages. And then when the 3rd one was queried, they sent the real IMSI. And that was a very successful way of unlocking for a while, so they fixed it. It's a very different, a lot of times when you get a lot of harassment from people when SIM interposers come out and you don't have an update to UltraSnow, but they're dealing with a fundamentally different interface than we are. They're dealing with the SIM interface, which is not an AT query kind of thing. Well, in some respects it is, but they have a very limited set of things that they're allowed to do, obviously, with the baseband. They're not allowed to control the baseband, but they're allowed to interact with it. We, for a long time, up until 02.28 was about to be released, we were working on a SIM interposer that, instead of playing tricks with the network, we were actually causing the baseband to crash using an exploit that we could deliver through the SIM card, as opposed to through the AT interface. And we were working on it for a while, and at the end of the day, it turned out they fixed it. And we saw it, actually, here are the messages, and remember those hidden change logs that were in the baseband. We saw, and our hearts fell when this update came out, because they were naming the exploit already, so there's something going on there, but they fixed the crash before we were able to deploy that unlock. And around that time is when we stopped getting the change logs too. If you read the iOS Hacker's Handbook, the very last chapter is Ralph's chapter on the baseband. He's got a pretty good example of going even further, not just fooling around with the SIM card, but going off and being the network and being a malicious network and causing the baseband to crash. And then in this case, he was able to use some standard AT commands to turn on the microphone and do remote eavesdropping of somebody, all initiated through a network that you didn't know was hostile. You walked into this network and joined it, and it attacked your phone. So the next, the remainder of the talk is sort of all related to tickets. There's all sorts of tickets that are going on nowadays in the baseband, at least in Apple's baseband. The first kind of ticket is this activation ticket, which at the end of the day is interesting. So for the longest time, let me get my drink of water. All of us were scratching our heads trying to figure out how long this PIN code, how long this normal unlock code was for the Apple basebands. Because we all knew that every time you had a baseband, you could always unlock it with this. If you were given the correct NIC code from the carrier, you could enter this one command, and they would go off and verify that, in fact, you knew this secret that only the carrier should know, and sure, you can go off and set this flag that says you can connect to any SIM card, and that's your unlock, your permanent unlock, which happens, when you pay your subsidy or meet your other requirements. So there is all this code, and the reason we were thrown for a loop is all this code is there in the baseband, and we could see the verification going on, we could see all the cryptology going on. But at the end of the day, it turned out all this time, even going back to the 3G, they were completely ignoring the results of the unlock. So even if we brute forced the NIC unlock key, it wouldn't have done any good because there's just they didn't simply accept the baseband from Infineon, they modified it. And in this case, they modified it to ignore any successful, well, I don't know if they explicitly ignore it, but they effectively ignore it. So what they do instead is this something very, very different. It's activation tickets. And it's very unlike a permanent unlock because if for some reason you're separated, you're isolated from the earth or from Apple, and you powered up your phone, and you had just restored it, even if you, all that time before that had been unlocked, or even talking to your own locked carrier, if you don't have an activation ticket, all communication is cut off. You don't get to talk to anybody. And so the activation ticket exists in all iPhones, and they're just, basically the only way they differ is the tables that are in that ticket. And you can't just edit, it is a text file in the end because everything can be reduced to a plist with Apple. So you can go off and edit the text file, which is in effect editing a binary, but you can't change it arbitrarily because it's signed. It's just using standard public key encryption stuff to make sure that the baseband is able to detect if you've tampered with the ticket. And so, Apple, just at the end of the day, their activation server is sitting off in the cloud. They go off, they see the ticket request coming from your phone. It contains your personalized information, your IMEI, your baseband chip serial number, all that sort of stuff. They look you up in a big database and they create this ticket and send it back to you after signing it. I'll show you an example. This last point, it turned out, not only on the i4, but on the earlier phones too, you couldn't simply just, when you look at the activation ticket after it's decrypted, it's pretty obvious that there are tables in there because there's a lot of lack of entropy, so you can sort of figure out the format of the ticket. But for the longest time, we didn't have insight into the content of the ticket because it's encrypted using information that normally only the baseband has about various IDs on its motherboard. Here's in this case, it's an iPhone 4 activation ticket. And it's just an arbitrary well, I think it's only an arbitrary format. It doesn't look, I don't recognize it as any other standard. But you can see there's basically some certificate stuff, some signature stuff, but the stuff that's highlighted in blue, a lot of it is actually optional. You're not even required to have all these fields. But usually the tickets do have it. The ICC ID is your SIM card number. IMEI is your iPhone's serial number, in effect. Thumbprint is that information I was talking about that's unique to your baseband, only he knows what it is. But the real payload in the ticket, that stuff is checked. It's required to match your information if it's there. But really what it all comes down to is all these IMSIs that are at that variable length field at the end of the ticket. And here on the bottom, I've shown you an actual dump of my decrypted ticket. And you can see if you look at an IMSI is composed, the first 6 digits are these yet more acronyms, MCC and MNC. So these are all the carriers that an AT&T phone should be able to talk to, all the networks that an AT&T locked phone should be able to talk to. And you can see there is plain as day, I'm allowed to talk to those 5 networks, and they do wildcarding. So you can see that the E in this case is just a flag for any digit. And it's a hex encoded value. Oh, I'm saying it wrong. But you can see it's BCD. So you can clearly see the 310, 150. And E in this case is just a flag for any digit. So you can see I'm matching an IMSI, which is really of length 6 plus 8 or 13. And you can see I'm just doing a wildcard match up until that F. And I'm very much louder all of a sudden. I'm not showing, the simplest ticket you can have is everything is E, right? And in fact, that is what an unlocked activation ticket looks like. You don't even go through, it's shorter than a locked activation ticket because you just wildcard all IMSI values everywhere. The nice thing about the iPhone 4S is if you have one, you can go off and examine the activation ticket yourself because they do not encrypt it anymore. I'm not sure why. And not only that, but they use ASN.1, which is a standard way of sanely controlling data that can be of arbitrary lengths, arbitrary fields, and all that sort of stuff. So it's a very standard thing in cryptography, and probably doing a disservice to it. But everything nowadays, and that's what that third comment is. Nowadays, even if you're not even talking about baseband stuff, all the AP ticket stuff, everything that goes on, anywhere you get anything signed by Apple, it's always coming back in this ASN1 format. So it's pretty interesting. You could see all these signed hashes coming back at you. I'll show you an example in a second. So this SAM unlock made the rounds recently, and it was using this software called SAM, which has actually been around for a long time. It has to do with faking the phone into letting you even see the home screen. But somebody found out that if you played enough games with the server using SAM, you could apparently fool the server or confuse the server, the activation server. What was happening is they found out that if you sent a request using what your phone should be unlocked to, or locked to rather, as far as the IMSI, but then you put your ICC ID in the ticket, so you do a sort of a mishmash of real and fake information. It sort of sounds a little bit like turbo sim, but it's not. What would happen, for some unknown reason, the server was hitting some unexpected problem on the server end, and you could find that if you now requested a real ticket using your real IMSI and your real ICC ID, that it would just happily just give it to you. And so some state was being kept on the server that was helping you unlock your phone. And it was all software-based from your point of view, and it was a server-based error from their point of view. The only problem with that bug, and they closed it within 4 or 5 days. A lot of people had been stuck with a locked phone for a long time, so I think a lot of people jumped on that ship. The only problem with it is because of the funny nature of the bug, you're actually tied to that one SIM card. So you got your unlock, but you only unlocked to that particular SIM card. So if you went to your cellular provider and switched SIM cards, it wouldn't work in your phone, even though it's the same carrier. So you can see this is, what is this? So this is my normal, again, this is the ASN.1 format of my normal locked AT&T phone. And of course, you could see the IMSI listed there in the same sort of format. And then here is the result from a SAM activation ticket. If you go off and decode it using ASN.1, you see these fields. And I've changed some of the numbers, but you can see that unlike a normal ticket, it has none of the IMSI numbers are wildcarded. It's very specific to that one SIM card. And also the ICC ID, which isn't even present on a normal activation ticket, is now present in this SAM ticket. So you could obviously see that SAM is really confusing the server and making it do stuff it never would do. But the nice thing about this ticket is it's good. It's signed by Apple, and the baseband trusts it, and it's good until the certificate that came with it expires, which is 3 years. All right, so switching topics. Let me see what I'm going to skip because I don't want to go too far over. Um, let's see. For the longest time, for all the early models of the phone, you were not allowed to downgrade your baseband, presumably because you didn't want to. They didn't want you to be able to go off and do a software unlock with a baseband that had been fixed. This is not enforced, obviously, by hardware. It's just a policy that they implement. Every time you use some kind of emergency mode to talk to the baseband, it knows enough about who you are. You sign your request, you sign your programs that you're asking it to run, and it knows enough to verify it. So the emergency bootloader that you send up is the agent that's in charge of saying, I'm not going to allow a downgrade. So what happens during a normal upgrade of the baseband, the baseband is sort of, the CPU is sort of stopped very early in the process. It's spoon-fed over the circuit port. It's spoon-fed a binary that can come from Apple at any point. They can create this binary and sign it because that's what Apple does. They can sign things. It's unlike the baseband, which is operating partly from flash and partly in memory. The emergency bootloader just sits in RAM, safely in RAM, does the funny hardware things it needs to do to erase the flash and reprogram the flash. So, and it's the one who's deciding whether or not to allow the flash in the first place. And early on, you could make it not realize that it was a bad version until late in the game, so at least you could erase it, but you couldn't end up flashing it, but sometimes just erasing the baseband is good. And the 3G, the very first version of the 3G had a bootloader bug, which was basically, it allowed you to affect that decision. You could just patch the EBL essentially and not make it care about what version you're about to flash. Fuzzy Band is the Cydia Store app that implements the exploit. They fixed it in 5.9. In fact, if I recall correctly, it wasn't until we saw the bootloaders that were coming with the new 5.9 phones that we did a compare against the 5.9 bootloaders against the 5.8, and it just stuck out as clear as day. There's only literally like 10 bytes that change between the two bootloaders, and it's just pointing right to the bug. And this is the bug. I still don't actually know what source code compile could have caused this, but rather up top it's checking that there is a signature in a certain location. And what it wants to do in this bottom check is sanity check the address and the length of the bootloader, but it's completely botched. It ends up accepting any length bootloader, any address you could write to, and any length except for the expected length. So it's a really weird bug. So the only trick about this exploit was that you needed to have a valid signature at the location. And it turned out you could just you could rob the signature from another part of the baseband file and just stick it in this place where the EBL signature is supposed to be. And that was enough to satisfy the top check. And then let the bottom check do its erroneous thing. And you can see this is just a fixed version. This is the original code, and this is what happened in the new iPhone 3G, and it's just, 10 or 20 bytes of difference. Starting with the iPhone 4, they don't care so much about preventing downgrades. They care more about personalizing your restore so that you can't replay restores. This is very similar to what happens on the AP side of things. There are BB tickets, baseband tickets that are very similar to AP tickets, the application processor tickets. I'm not going to go through this stuff because I don't have time. I don't have time, right? Oh, I am? Okay, I'll talk about it a little bit. How much time do I? 5? Oh, okay. That's not much time. What's that? Okay. So the BB ticket is just basically just like the problem is that all sorts of, like I said before, there's all sorts of tickets nowadays. So the activation ticket is a very different thing from this baseband ticket. Activation ticket is what gets you to talk to your towers around you, and the baseband ticket is what allows you to flash a certain version of the baseband. But it's all using the same sort of thing nowadays. It's all, I don't have a picture of it, but it's all using an ASN.1, container that's signed by Apple, specifying what versions of things you're allowed to talk to, restore to. It's also verified in every boot. Oh, one difference between the baseband ticket and the AP ticket is that for whatever reason they don't bother. There's some randomness that's added to the request to the server that gets signed by Apple. For some reason they don't bother to check that value, the random value they put in the ticket, is matches what you originally asked for. There's one place where they do check that on the AP side, but then at that point they stop caring. Baseband is not like that. The baseband has some way of storing the original randomness that it put in the request, and it checks it every time. It verifies not only that the ticket is signed correctly and integrity is matched, but it verifies that the field that contains the nonce matches the nonce that was used that one time during the restore. iPhone 4S is really interesting. I'm going to end on these two slides rather than go on to this other crap. iPhone 4S is really interesting from a tinkerer's point of view, because all of a sudden they don't have flash anymore. They don't have flash for the baseband. So normally, whereas all the other phones up till now, there was a certain section where the bootloader was, a certain section where the baseband was. There was a chain of activity that happened during the boot. Everyone's verifying the next stage and all that crap. It turns out with the iPhone 4S, there's no flash. And so it just wakes up from reset and sees no flash. It doesn't know what to do, so it just sits there in this sort of emergency service mode waiting for something to do. So the AP side of the phone has to, at this point, come in and spoon feed it the image that it would normally be taking from its own flash and the other earlier devices. So it's kind of interesting. It's very useful from tinkerer's point of view, because you don't have to worry anymore about, if you wanted to experiment or fuzz the bootloader or look for bugs or try some ideas out, before you always had to get through the whole flashing step, which itself is a whole bunch of issues with signing and bypassing signing. Turns out with the iPhone 4S, it's sitting there in this sort of semi-emergency mode. You can just sort of spoon feed it devices, images, and test your ideas on this baseband that's not going anywhere until you spoon feed it something. The one place where they did, you can see in the comm center of the iPhone 4S, they added one very specific, very important step to the normal Qualcomm boot, which is they require, one of the very first things you must do when you start talking to the baseband is provide it yet another ticket. I don't know if I even say the word ticket here. Yeah, so it's a different form of a BB ticket, but again, it's an ASN.1 message that's signed by Apple. The baseband knows how to verify it's real. And you can't do anything. It's unlike a Qualcomm baseband in a lot of ways, because a Qualcomm baseband, normally when it sees that there's no flash, no storage, or if it detects that the flash was tampered with, it'll go into this emergency mode where you can now interact with it with less restrictions. But Apple added this bunch of Maverick code to it, so you can't even do some core stuff that you could do with a Qualcomm baseband that's normally otherwise in an emergency mode like this one is. The only other funny thing about the iPhone 4S flashing process is that because there is no flash for the baseband to store the BB ticket, you need to keep feeding the BB ticket to it for every single boot. Not only do you need the BB ticket to do the reflash of what version should be being used, but now you need to spoon feed that ticket on every single boot before you even give it some of the later stages of bootloaders. They happen to save that. That's one funny place on the normal AP side of the phone. They modify the root file system to include that BB ticket. That was never done before the iPhone 4S. It was never needed to be done, because you could always store that in the flash. What we're seeing with the Qualcomm baseband is, they have their own set of debug features, and Apple went ahead and used the same stupid bit mask to disable all those debug commands that would normally be allowed by any other Qualcomm baseband. There is a bug that we found early on in Apple's implementation, so yay, Apple made a mistake again, where we could get access to the boot ROM bypassing some of the checks that were normally done by the new Maverick protocol. So I'm going to close actually on these last few points. This is a really good reason to start fooling around with the baseband again. I've sort of talked to these points already, but it's a really nifty way to tamper with the process very early on in the boot stage. So there's a lot of, you can go off and read all you want about Qualcomm. These are the different Qualcomm boot stages, but you can, because there is no flash, you can go off and much more quickly, without worrying about bricking your baseband, you can go off and experiment. So I encourage you, if you're at all interested, to look for bugs an iPhone baseband to buy an iPhone 4S and do that. The downside is that with all this Qualcomm stuff, the AT parser is gone. That humongous YY parse code is all gone. So now you have to start learning how Qualcomm comm centers should be talking to the baseband. So it's a whole different thing. It's not a simple serial interface. You're not typing AT commands at it. You need to understand the protocol. But still, it's a pretty unexplored environment, I think. So jump if you're interested. Every boot is an emergency boot. That's the takeaway from that. We are seeing that with the iPad 3 baseband, for those iPad 3s that have cellular, we are seeing that the Qualcomm code is taking a drastic turn. I don't know if it's temporary or what, but they're starting to use their hexagon DSP architecture, and they're taking over a lot of the baseband utility core code that would normally be done by ARM, and using it with hexagon. So again, this is another reason to start tinkering with the iPhone 4 baseband, because all this stuff I think is about to change. And so anytime the SDK changes, anytime the whole tool chain changes, you hope that there's a whole new set of bugs that pop up. And not only is the tool chain changing, but the whole architecture, the whole instruction set architecture is changing. So again, another reason to start fooling around. I'm gonna skip all this stuff. This is just, this will be online. These are the different ways that you can brick a phone other than the iPhone 4S. These are the reasons for it. And that's it. Thank you.
Thank you.
Sure.
Mike.
Oh, we're gonna ask questions?
You can Mike. Yeah.
Oh, does anyone have questions?
We can do one or two questions, if there are questions. If not, I'm sure you can talk to MuscleNerd after, and we'll go continue with our next presentation.
Great.
Thanks a lot.
Thanks. That's all right. I didn't like this last few slides anyway. I didn't like this.